Voltaic cells. When two half reactions occur at electrodes in separate beakers, a voltmeter placed between them shows a difference in SRP. The difference is due to the electrode with the lower SRP generating excess electrons due to oxidation, while the other electrode has a deficit of electrons due to reduction. The electrode with lower SRP is the anode, and that's where the oxidation occurs. The electrode with the higher SRP is the cathode, and that is where reduction occurs. Here, the compartment on the left has a zinc electrode in a solution with zinc ions, zinc nitrate here. The compartment on the right has a copper electrode in a solution with copper ions from the copper nitrate. The two reduction half reactions are shown. Now these are both reduction. Look up the SRPs for each reaction on the chart provided earlier and determine which of the electrodes is the anode and which is the cathode. And we'll have the answer on the next slide. The SRP for each electrode is shown below. Here's the SRP. Here are the two reduction reactions. Now we know one is going to be oxidized, okay? But we're still just going to show the reduction reactions because that gives these numbers here. So since zinc has a lower SRP, it is the anode. So now we fill in the anode and oxidation. And the voltmeter reads 1.0 volts since it reads the difference in voltage. It'll be the SRP of the cathode, which is 0.34, minus a minus 0.76. And that's from the anode. Take the difference and you get E cell is 1.10 volts. We replace the voltmeter by a wire. Electrons flow from the anode to the cathode. That's due to oxidation at the anode generating excess electrons, while reduction at the cathode requires those electrons. That's reflected in our reversing the reaction at the anode, right here. On the previous slide, we showed what it would be like if it was reduction, but since we know it's oxidation now, we reverse the reaction. And it will be generating electrons. The 2e over here, then the cathode picks them up over here. Summarizing that, the oxidation reaction generates electrons within the anode, right in here, and zinc 2+ ions within the solution, down here. And here's the reaction. So the solid zinc turns into zinc 2+ aqueous, which means it's dissolved in the solution, plus 2 electrons. The reduction reaction consumes electrons within the cathode, right in there. That's where it's going on. And Cu2, copper 2+ ions within the solution, right here. It takes up these aqueous ions, picks up the electrons, and builds up more copper there. As these reactions proceed, the solution on the left, which is the anode, I'll just highlight that up here, anode, and here's cathode on the left. The one on the left will develop a positive charge since oxidation generates zinc 2+ ions. So you've got 1, 2, 3, 4, 5, now you have many more. So this side now is a plus. And by the way, this drawing is not to scale in terms of the number or size of ions. It's just to illustrate what's happening. The compartment on the right now develops a negative charge since the reduction is consuming these 2+ ions, so we now have a negative charge. The reactions would stop at this point since the charge in the solutions, we're dealing with the solutions now, would attract the electrons back to the anode. So the electrons were starting to go like this, but now I've got a big positive charge on the left. The electrons are going to flow right back, because the solution, the positive solution over here, is attracting the electrons back, and the negative solution over here is pushing them away. So everything stops. What if we wanted to keep going because we're trying to make a battery here? We have to restore the neutrality of each solution so it doesn't stop the electron flow. How are we going to do that? Well, let's move on. We maintain the neutrality in each compartment by connecting them with a salt bridge. This is a glass tube filled with a gel which contains a salt whose ions are free to move. The gel is held in place by ion-permeable plugs at both ends of the tube, so the gel can't get escaped, but ions can move back and forth. The salt in the bridge is represented by the purple color, which I already circled. Salt bridges use soluble ionic salts such as potassium, sodium, or ammonium nitrates. The ions from the salt bridge will neutralize the charge accumulated in the anode and cathode compartments. These salts must be chosen so that they have no interaction with other ions and are always soluble in aqueous medium. In this case, the salt potassium nitrate generates nitrite and potassium ions. Red indicates the negative ions, and that's coming from the salt bridge. And black indicates positive ions, also coming from the salt bridge. The positive ions are attracted to the solution with a negative charge, which is this solution over here. Negative salt ions are attracted to the solution with a positive charge, which is this solution over here. The neutrality of the compartments is now maintained. As the reactions proceed, electrons flow, so the electrons can keep flowing like this, while salt ions maintain the neutrality of each solution. So if you add all these charges up, you get 0, and you add all these up, you get 0. The flow of charge is shown here, with the green arrows next to the wire indicating the flow of electrons with their negative charge out of the left compartment and into the right. The offsetting flows of ionic charges are shown next to the salt bridge, which is in purple, with the negative ions, nitrate, indicated by red, entering the left compartment to replace the charge taken away by the electrons, and positive ions, the potassium plus, indicated by black, entering the right compartment to offset the gain in negative charge from electrons entering the right compartment. The lengths of the arrows correctly show that the flows of charge are exactly offsetting. 3 additional notes. The ions that flow from the salt bridge are different from the ions in either of the solutions. The salt must be chosen so that neither of its ions react with the ions in solution. If they were to react, the cell would cease to function. While ions in the salt bridge maintain an electrical connection between the two solutions, ions do not flow between the compartments. They're not going from here to here or here to here. Ions just go from the salt bridge into their respective compartments. So nitrates go here, K pluses go here. As oxidation occurs at the anode, the electrode is dissolved into zinc cations. The size and mass of the zinc anode is reduced. As reduction occurs at the cathode, copper ions come out of solution to become part of the cathode. The size and mass of the cathode is increased. And on this one, the size difference in the above electrodes is greatly exaggerated, right? You can see the zinc really shrinking and the copper getting very much bigger. That's just to make the point.